Hi, today we want to look at the derivatives of inverses. So do you remember what an inverse is? An inverse undoes whatever a function does. So let's start off with a function and an inverse that are pretty easy to work with. So how about a line? That's a pretty easy function to think about, the inverse. So if we have a function 1/3 of x plus 1, then the inverse, so this thing takes its input and divides it by 3 and then adds 1 onto it. So the inverse of this thing, and you worked with these in college algebra. I'll remind you real quick, to find the inverse, you just reverse where the x and the y are. So replacing the f of x with a y, and then to find the inverse, you switch where the x and the y are, and then solve the equation again for y. Do you remember this? So if we subtract the 1 over to the left, we get this. And then I guess we need to multiply everything by 3 in order to solve for y. So the inverse looks like this. Do you remember this? I hope that you do. It's not hard to think about. So that's reminding you how to find an inverse. And again, we divided by 3 and added 1, and it turns out that the inverse subtracts 1 and multiplies by 3. So f inverse really does undo what f did, right? So, okay. So what do the derivatives look like? Well, here's a theorem that we're going to use, and I'm not going to prove this, I'm just going to ask you to trust me that this thing is actually true. The proof is kind of long and complicated, so if you're willing to trust me, then we can keep it short and not complicated. So the theorem says that the derivative, oh wait, hold on. The theorem says that if f and g are inverses of each other, then their derivatives are related in this way. One moment, something's in my throat. Okay, so does this thing hold with our pair of lines here that we determined to be inverses of each other? So if we call this thing g, so here's f 1/3 x plus 1, and then we determined that the inverse, and I'm going to distribute this 3, so 3x minus 3, then f prime is just equal to 1/3, right? And g prime is just equal to 3. And the theorem says that the derivative of f is equal to 1 over the derivative of g evaluated at f. But g is just a constant. I'm sorry, g prime is just a constant, so it'll just be equal to 3 everywhere. So at least in the case of a couple of lines, the theorem holds, right? So let's look at a slightly more interesting case. So in the video about the derivative of log x, I plotted a bunch of, well, I was using the central difference approximation to numerically try to come up with the derivative of log x. Here, let's use what we know about log x as an inverse function. So if f and g are inverses of each other, and f is the log of x, What's g? What's the inverse of log x? Why don't you pause the video for just a moment and Google it. Inverse of ln x. I'll wait here. Did you do it? Did you Google it? It's e to the x. Yeah, it's e to the x. Okay, so let's see if we can use this thing to figure out what the derivative of log of x is. The work that I did on the previous video suggests that the derivative of log x is equal to 1 over x. So let's see what we get if we try to use this thing. First of all, g prime is just e to the x, right? We love e to the x. And so let's try to put all of this together. So f prime I'm supposed to do 1 over whatever g prime is evaluated at f of x. So g prime is e to the x. So I want g prime of f of x, and f of x is log x. What is g prime? G prime is the function that takes its input and uses it as a power on e. And here we have the input of log x. Well, what's e to the log x? If they're inverses of each other, then when you do one and then the other, you should just get back the original input, right? So e to the log x, that's the definition of what an inverse is. So e to the log x. In fact, try this. Plug it into your calculator. Can you do that? Well, I'll do a couple of them on my calculator and you'll see what I mean. Looking at e to the log x. So if we do e to the log of 2, oh, we get 2. Ooh! If we do e to the log of 7, we get 7. How about e to the log of 429.2? Oops. Yep, you guessed it, 429.2. So e to the log x. Yeah, 1 over x. So when when the function is log of x, the derivative is 1 over x. So this agrees with what we saw in the previous video, so that's all good. So we have one more set of inverses to look at. So what about arc sine, arc cosine, and arc tangent? Do you remember what these things are? If you need to pause the video and go and Google these so that you can remember what these things are, you can just Google inverse trig functions, and there's lots and lots out there. Anyway, to find the derivatives of these things, we're going to need the derivative of sine and cosine and tangent. And the way this lesson is set up, you're going to be looking at those in the preview activity and also in the in-class activities. So, but I'm going to tell you what they are now. Spoiler alert! So here they are. Oh, that's loose. And again, we're going to be working on these over the next couple of days. So you're going to do some work to convince yourselves that these are really the derivatives as I claim that they are. You would trust me anyway, wouldn't you? But yeah, anyway, we're going to be working on these. So how can we use all of this together with this thing to come up with the derivatives of arc sine, arc cosine, and arc tangent? Okay, so let's look at arc sine first. So if f of x is arc sine, and if f and g are inverses of each other, then what's g? G is the sine of x, right? That's what arc sine is. It's the inverse sine function. They're inverses of each other. And then we'll also need the derivative of sine, cosine. Okay? And then when we use this formula to try to come up with the derivative of f, what do we get? We want g prime evaluated at f, and f is arc sine. Now g prime is cosine. Oh my God, what is this? What does this mean? Well, in order to find my way through this, I need to draw a picture of a triangle so I can see what's going on. So let's just, I'm pulling this apart a little bit, and then we're going to use this right triangle to try to figure this out. If y is equal to arc sine of x, that's this part in here. This is the same as saying that x is equal to the sine of y, right? Oh, that tells me that y is an angle, because you only take the sine and the cosine and the tangent of angles, right? So let's make this angle here, let's make that equal to y. And the sine of this angle is equal to x, and the sine of an angle is equal to the ratio of the opposite to the hypotenuse, right? So the opposite to the hypotenuse are in a ratio of x to 1. And so if this is the angle, this is the opposite, and this is the hypotenuse, right? Okay. And then from the Pythagorean Theorem, can we get the length of the other side? This side over here, so I know that x squared plus b squared is equal to 1 squared, right? And I just want to write down what b is. So b squared is equal to 1 minus x squared. So b is equal to that, right? Because I want to do this all in terms of x. So this b can be replaced with this. All right, how does this help? Well, this thing that we came up with here says that the derivative of arc sine can be gotten by figuring out what this is. And so we've taken this thing and we've replaced it with y. And so from our picture, 1 over the cosine of y is an angle, and I want the cosine of it. Now the cosine is the adjacent over the hypotenuse. Do you remember this from trig? So for this angle, this is adjacent, and this is the hypotenuse. Is that what I said before? Well, that's what it is. Adjacent over hypotenuse. So 1 over the cosine of y is 1 over the square root of 1 minus x squared divided by 1, and dividing by 1 doesn't do anything. And that is the derivative of arc sine. Super crazy, right? The derivative of sine and cosine kind of relate to each other back and forth, but the derivative of arc sine is this algebraic thing that doesn't have any trig pieces in it at all. You can go through the same kind of process here for the derivative of arc cosine. And it looks exactly the same as the work that we've done here. You get the negative of the result for the derivative of arc sine, which kind of makes sense because of this thing here. I'm not going to go through all of that. You can just take this and run with it. Let's look at tangent, though. So if we run through this procedure with tangent, so if f and g are inverses of each other and f is arctan, then g is just going to be tangent, right? And you'll see in class this week why this is true, but for now I'm just going to use it. And then according to the formula that relates the derivatives of inverses, the derivative of f is equal to 1 over the derivative of g evaluated at f. So g prime evaluated at f, and g prime is what? Secant squared. So we get another one of these, what should we call them? Trigonometric puzzles, right? So let's draw a triangle. So if I stick the angle y down here, this says that the ratio of the legs of the triangle, the opposite to the adjacent, they are in a ratio of x to 1, right? So this is x and this is 1. And then according to the Pythagorean Theorem, the length of the hypotenuse is this, right? Mm-hmm. Okay, so f prime is 1 over the square of the secant of y. And you remember from trig, right? This is the same thing as the cosine of y squared. And cosine is the adjacent over the hypotenuse. So for this angle, adjacent is here and hypotenuse is there. Right? And squaring it all up, we get the derivative of arctan. So there you have it. The derivatives of arc sine, arc cosine, and arctangent, all based on this formula that gives us the relationship between the derivatives of a couple of functions that are inverses of each other.